Hello, dear students. Welcome to the channel and very welcome to this playlist in which we are discussing about instrumentation and sensors. So, in previous class, we have discussed about different sensors, what exactly sensing means, and we have discussed about some very common and some very uncommon type of sensors, starting from the strain gauge, pressure gauge, uh, basic sensors, until we have till we have moved towards very rare sensors, some for measurement of flow, piezoelectric materials, piezoresistive materials. We have saw ultrasonic sensors. We saw nuclear sensors, and even microelectric sensors as well. So if you want to learn about the different type of sensors, the link will be flashing on the top right hand side corner of the screen. You know what to do, just click on it and you will be redirected to that video. If you have already checked out, in that case, let's discuss today's class. Today we are going to discuss about different type of instruments. In the very first video we have discussed about what exactly instrumentation and measurement is, and in continuation to that we are going to discuss the different types of the instrument in detail today. So based on different applications we can subdivide the instruments in separate classes based on different criteria, and they help us in broadly establishing several attributes of particular instrument like accuracy, cost, precision, applicability, adaptability, or the strength to different applications, right? So first classification is active and passive instruments. So an instrument is divided into either active or passive instrument based on whether the instrument output is entirely produced by the quantity being measured, or whether the quantity being measured simply modulates the magnitude of some external power source. Let's take an example and learn that. For passive instrument, it's a pressure measuring device. As you can see in this image, this is a passive pressure gauge or pressure gauge. It is a passive device, and the pressure of the fluid is translated into the movement of the pointer against a scale. So the energy ex- expended in moving the pointer is derived entirely from the change in the pressure measured, and there are no other energy inputs to the system at all, right? And then we have the example of active instrument, which is float type petrol tank level indicator. As you can see here, this is the float type petrol tank level indicator, which indicates the level of the petrol. Here's the float, here's the pivot, and this is the output in form of the voltage. So here the change in petrol level moves a potentiometer's arm, and then the output signal consists of a proportion of external voltage source applied across the two ends of the potentiometer. So the energy in the output signal comes from the external power source, and the primary transducer float system is merely modulating the value of the voltage from its external power source. So that's why it is included as an active instrument. So in active instrument, always remember the external power source is usually in electrical form, but in some cases it can be of other forms like pneumatic or hydraulic as well. And one of the major differences between active and passive instrument is the level of the measurement resolution that can be obtained. So with very simple pressure gauge, as you saw, the amount of the movement made by the pointer for particular pressure pressure change is closely defined by the nature of the instrument itself. But it is possible to increase the measurement resolution by making the pointer large and such that the pointer tip moves through a longer arc. So the scope for such improvement is clearly restricted by the practical limit of how long the pointer can conveniently be. And in an active instrument, however, adjustment of the magnitude of the external energy input allows much greater control over the measurement resolution. The scope for improving measurement resolution is much greater incidentally, and it is not infinite because of limitations placed on the magnitude of the external energy input in consideration of the heating effects and for safety reasons as well. Now, passive instruments are simple in the construction, where active ones are more more complex, and because of that, active ones are cheaper to manufacture, and therefore the choice between active and passive instrument for particular application involves careful balancing the measurement resolution requirement against the cost. Then with null type and deflector type instruments, so the pressure gauge just mentioned is a good example of the deflection type instrument as well, where the value of the quantity being measured is displayed in terms of amount movement of a pointer. So see, here we have the pointer piston. An alternate type of pressure gauge is a dead weight gauge. The dead, the dead weight gauge is visible here, which is a null type instrument. And in null type, what happens? The weights are put on top of the piston until the downward force balances the fluid pressure. The weights are added until the piston reaches the datum level and known as the null point. The pressure measurement is made in terms of the value of the weights needed to reach this null position. The accuracy of these two instruments depends on the different things. For the first one, it depends on the linearity and calibration of the spring, while the second one it relies on the calibration of the weights, as the calibration of weights is much easier than the careful choice of the calibration of the linear characteristic spring, which means that the second type of instrument will normally be more accurate. This is in accordance with the general rule that null type instruments are more accurate than the deflection types. And in terms of usage, the deflection type instrument is clearly more convenient. It is far simpler to read the position of a pointer against a scale than to add and subtract weight until the null point is reached. Right. So the deflection type instrument is therefore one that would normally be used in the workplaces, but for calibration duties, the null type instrument is preferable because it has the superior accuracy, and extra effort is required to use such instrument is perfectly acceptable in this case because uh, infrequent nature of calibration operations. Then the analog and digital instruments, we most of us are well familiar with it. Analog instrument gives output that varies continuously as the quantity being measured changes, and output can give have infinite number of values within the range that the instrument is designed to measure. The deflection type of the pressure gauge describes we have described earlier is a good example of analog instrument. As the input value changes, the pointer moves with the smooth continuous motion, and while the pointer can therefore be an infinite number of positions within the range of movement, the number of different positions that the eye can discriminate between is strictly limited, and this discrimination being dependent upon how large the scale is and how finely it is divided. Then we have the digital instrument that has an output that varies in discrete steps, and so it can only have a finite number of values. The rev counters, which shown here, is a fine example of digital instrument. Here we have the counter. So cam is attached to the uh, revolving body whose motion is being measured, and on the other revolution the cam opens and closes a switch. The switching operations are counted by electronic counters, and this system can only count whole revolutions and cannot discriminate any motion that is less than full revolution. So the distinction between analog and digital instruments has become particularly important with the rapid growth in the application of the microcomputers to automatically control the system. And any digital computer system on which microcomputer is but one example performs performs its computation in digital form. Then an instrument whose output is in digital form is therefore particularly advantageous in such applications, as it can be interfaced directly to the control of the computer, whereas analog instrument must be interfaced with to the microcomputer by an analog to digital converter, which converts the analog output signal from instrument into the equivalent digital quantity, and that can be read into the computer later on. And although this conversion has several disadvantages, but it is absolute necessity for analog devices. So firstly, A to D converter adds significant cost to the system. Secondly, finite time is involved in the process of converting an analog signal to a digital quantity, and this time can be critical to the control of fast process, where the accuracy to control depends on the speed of the controlling computer. Then the degrading speed of operation of the control computer by imposing the requirement for A to D conversion thus impairs in accuracy by which the process is being controlled. Then we have the indicating instruments and the instruments with the signal output. So last way in which instrument can be divided in between those that merely give an audio or visual indication of the magnitude of the physical quantity measured, and those that give an output in the form of the measurement signal whose magnitude is proportional to the measured quantity. So the class of indicating instrument normally includes all null type instrument and most passive ones. The indicator can also be further divided into those that have an analog output and those that have the digital display. A common analog indicator is a liquid in glass thermometer. Another common indicating device which uh, exists in both analog and digital forms is the bathroom scale. And the older mechanical forms of this analog type of instrument that gives an output consisting a rotating pointer moving against the scale, or sometimes rotating scale moving against a pointer. And more recent electrical forms of bathroom scales have digital output consisting of number of presented on an electronic display. One major drawback with the indicating devices is that human intervention is required to read and record the measurement. So the process is particularly prone to error in the case of analog output displays, although digital displays are not very prone to error unless the human reader is careless. But the instrument that has have a signal type output are commonly used as a part of automatic control systems. In some circumstances they can also be found in the measurement systems where the output measurement signal is recorded in some way for later use. So this subject is covered in upcoming chapters which we will be discussing, but usually the measurement signal involved in the electrical voltage, it can take other forms in some systems such as electrical current and optical signal or pneumatic signal or hydraulic signal, etc. Now let's see some of the static characteristics of instrument. Let's say if we have thermometer in the room and it is reading is showing a temperature of 20 degrees Celsius, then it does not really matter whether the true temperature of the room is 19.5 or 20.5. Right, such small variations around 20 degrees Celsius are too small to affect whether we feel warm enough or not. And our bodies cannot discriminate between such close levels of temperature, and therefore the thermometer with an inaccuracy of zero point 0.5 degrees Celsius is preferably adequate. But if we had to measure the temperature to certain chemical process, however, the variation of zero point 0.5 degrees Celsius might have a significant effect on the rate of the reaction to or even the product of the process. So a measurement inaccuracy such as less than zero point 0.5 degrees Celsius is therefore clearly required, and accuracy of the measurement is thus one consideration in the choices of the instrument for particular application. We have other parameters as well, like sensitivity, precision, linearity, and the reaction to ambient temperature changes are further considerations. But these attributes are collectively known as the static characteristics of instruments, which we are going to discuss right now, and they are given in the data sheet for the particular instrument. So you can check them while selecting a particular instrument or purchasing the particular instrument. It's also important to note that the values quoted for instrument characteristics is in such a data sheet only appear when the instrument is used under specific standard calibration conditions. Now, due allowance must be made for the variation in the characteristics when the instrument is used in other conditions. Now, let's see few of them: accuracy and inaccuracy, or measurement uncertainty, which is called. So, accuracy of instrument is a measure of how close the output reading of the instrument is to the correct value. So, it is more usual to quote an inaccuracy figure rather than the accuracy figure for an instrument. Inaccuracy is the extent to while reading might be wrong, and often the quote as a, often quoted as a percentage of the full scale reading of an instrument. For example, pressure gauge ranging from 0 to 10 bar has quoted inaccuracy of plus or minus 1% of full scale, which means then maximum error can be expected of in any reading would be zero point 0.1 bar, which means that when instrument is reading 1 bar, then it is possible error is 10% of its value. For this reason, it is an important system design rule that instruments are chosen such that the range is appropriate to the spread of value being measured. In other than the best possible accuracy is maintained, and in instrument readings, thus if we were measuring pressure with expected values between 0 and 1 bar, we would not use the instrument with the range of 0 to 10 bar, right? So the term measurement uncertainty is frequently used in place of inaccuracy. Then we have the precision, repeatability, or reproducibility. So first let's discuss about the precision. Precision is the term that describes the instrument's degree of freedom from random errors. So if the large number of readings are taken of the same quantity by high precision instrument, then the spread of readings will be very small. And often precision is thought incorrectly confused with accuracy, but accuracy and precision are totally two different things. High precision does not imply anything about measurement accuracy. Precision instrument may have a low accuracy, but low accuracy measurement from high precision instrument are normally caused by bias in the measurement, which is removable by recalibration. Then we have the repeatability. Repeatability and reproducibility mean approximately the same, but are applied in different contexts. Like repeatability describes the closeness of output reading when the same input is applied repetitively over a short period of time with the same measurement conditions, and same instrument and observer with same location, same condition of use maintained throughout. And what is reproducibility? Reproducibility describes the closeness of the output reading for the same input when there are changes in the method of the measurement. or observer or measuring input, location, condition of the use and time or time of measurement. So both terms thus describe the spread of output reading for the same input, and this spread is referred as a repeatability if measurement conditions are constant, and a reproducibility if measurement conditions vary. Now, degree of repeatability or reproducibility in measurements from instrument is an alternative way of expressing in precision. Now let's see what is tolerance. So tolerance is the term that is closely related to the accuracy and defines maximum error that is to be expected in the sum value, but it's not strictly speaking a static characteristic of a measuring instrument. It is mentioned here because the accuracy of the sum instrument is sometimes quoted as a tolerance figure. But when used correctly, tolerance describes maximum deviation of the manufacturer component from some specific value. For instance, crankshafts are machined with the diameter tolerance quoted as so many microns. Electric circuit components such as resistors have a tolerance of perhaps 5%, and one resistor chosen at a chosen randomly from a batch having nominal values of 10,000 watts or 1000 watts and tolerance of 5% might have an actual value anywhere between 150 watt to 150 1050 watts. So here you can see low precision, low accuracy, right? So everything is scattered. We have when we have high precision but low accuracy, then everything would be uh, constructed or compiled together, but still not on target. But the robot with the high precision and high accuracy means it is hitting it on target and hitting it repeatability with high precision. Then we have the range or the span, which is defined as the minimum or maximum value of quantity that the instrument is designed to measure. Pretty straightforward. Then we have the linearity. So normally described, the output reading of the instrument is linearly proportional to the quantity of quantity that's being measured. And see here the X marks which are being marked here shows the plot of a typical output reading of the instrument when sequence of the input quantities are applied to it, and normal procedure is to draw a good fit straight line through axis, as you can see in the image, right? So the non-linearity is then defined as the maximum deviation of any of the output readings marked S from this straight line, and usually it expressed as the percentage of full scale reading as well. And by the way, if your signal, if you are particularly talking about signal, if your signal satisfies the superposition theorem, then the signal is considered as linear signal. Then we have the sensitivity. Sensitivity of a measurement is a measure of the change in instrument output that occurs when the quantity being measured changes by a given amount, right? So basically sensitivity is the ratio of scale deflection to the value of measurement producing deflection. And because of this ratio, sensitivity of measurement is therefore a slope of the straight line drawn on this figure here, right? This slope indicates the sensitivity or gradient. And for example, a pressure of a 2 bar produces the deflection of 10 degrees in the pressure transducer. The sensitivity of the instrument is 5 degrees per bar, assuming the deflection is 0 with the 0 pressure applied. Then we have the threshold and resolution. So if the input to the instrument is gradually increases from 0, the input will have to reach at certain minimum level before change in the instrument output reading is of a large enough magnitude to be detectable. So the minimum level of the input is known as a threshold of the instrument, and manufacturers vary this specific threshold for different instruments. Some quote absolute values, whereas others quote threshold as a percentage of the full scale reading. And as we can see, as we can illustrate, a car speedometer typically has a threshold about 15 kilometer per hour. Means if the vehicle starts from rest and accelerates, no output reading is observed on the speedometer until the speed of the car reaches 15 kilometer per hour. Right, so that's the threshold for you. Then we have the resolution, and when an instrument is showing a particular output reading, there is a lower limit on the magnitude of the change in the input measured quantity of that produces an observable change in the instrumental output, just like threshold. But resolution is sometimes specified as an absolute value and sometimes as a percentage as well. Right. So, one of the major factors influencing the resolution of an instrument is how finely its output scale is divided into subdivisions. Using a car speedometer example one more time. So this is subdivision. This is a subdivision of typically 20 kilometer per hour or 15 kilometer per hour, and that means that when the needle is between the scale markings, we cannot estimate the speed more accurately than the nearest 5 kilometer per hour. Right. So this figure of the 5 kilometer per hour represents the resolution of the instrument. Then we have a sensitivity to disturbance. We are not going to fall in the details of it, but we are going to discuss the hysteresis. Right. See, this is the hysteresis curve. Right. And it illustrates the output characteristics of the instrument that exhibits hysteresis. So if the input measured quantity to the instrument is steadily increased from a negative value, the output reading will vary in a manner that shows this curve A. So this basically is the curve A. And if the input variable is then steadily decreased, then output varies in the manner that shows the curve B. Right. Now the non-coincidence between these loading and unloading curves is known as the hysteresis. Right. And two quantities are defined: maximum input hysteresis and maximum output hysteresis. These are normally expressed as the percentage of the full scale input or output reading respectively. And it's most commonly found in instruments that contain springs, like passive pressure gauge and prony brakes, which is used for torque measurement. It's also evident then when friction forces in the system have different magnitudes depending on the direction of the movement, like pendulum scale mass measuring device, or device like mechanical fly ball, right? That suffer hysteresis for both of the above sources because they have friction in moving parts and also contain spring as well. So hysteresis can also occur in the instrument that contain electrical windings formed round and around an iron core due to magnetic hysteresis in the iron. And we all know which device we are talking about, right? Transformers. Then this occurs in the devices like variable inductance displacement transducer, also known as the LVDT, and the rotary differential transformer, RVDTs. Then there is something called dead space, would be the final characteristic we are going to discuss today. So dead space is defined as the range of the different input values over which there is no change in output value. Right. Any instrument that exhibits hysteresis is also displays dead space. And some instruments that do not suffer from any sufficient hysteresis can still exhibit some dead space in their output characteristics, but the backlash in gears is typical cause of the dead space and result in the sort of instrument output characteristics is visible in this figure. So this is dead space. It doesn't work in this region, so that region is known as dead space. So backlash is commonly experienced in the gear set used to convert between translation and rotational motion, which is common techniques used to measure the translationary velocity, by the way. So these were all the static characteristics of instruments, and we have also discussed about different types of instruments in detail as well. If you have any doubts, any queries related to today's class, feel free to mention them in the comment section below. Any type of feedbacks or suggestions are always welcome. So if you have feedback or if you want to make me a video on some particular topic, you can mention that topic in the comment section below as well. I will try to answer all the comments as soon as possible and as many as possible. So I will be seeing you next time with a new topic. Till then, thank you very much for listening. Goodbye for now.